So on page 30, it was Sarah. Sarah was driving on the highway. And we had seen that this was a linear graph because she was on the highway. She was exhibiting constant rate of change. The two quantities were so we had time and distance. Which was the vertical or horizontal axis quantity?
Hours.
This was hours. So this was t was the time since she left home. In hours. Okay? That's our horizontal axis quantity. And then what was the vertical axis? Yeah, distance from home in miles. And we saw that she started at, when she had driven a half an hour, she was 25 miles from home. Is that right? And we also found her speed by taking the change in distance over the change in time. And her change in distance was 220, because up here she was at 4 hours, she was 225 miles from home. 245. Okay, so her change in distance was 220 over the change in time of 3.5 hours. Yeah, 4 minus a half. And we got 62.85, is that right? Okay. So, and we were examining these changes in time and changes in distance. So we can just, over here, we can make a little table here. If her change in time is 1 hour, what's the corresponding change in distance? Yeah, that's what speed means. It means how far you go. If it's miles per hour, it's how far you go every hour. So remember, the book's definition was that equal changes in time mean equal changes in the first quantity result in equal changes in the second quantity. So does it matter at what time we start looking at a change in time of 1 hour? We can start here at 1, we can start at 2, we can start at 2.5, and then we can take a change of time, an additional amount of time of 1 hour, and no matter where we start, the additional distance will always be 62.85. That's constant rate of change. Equal changes of 1 hour will always make a change of distance of 62.85. Similarly, what if we say an additional time amount of 2 hours? What will her change in distance be? It'll be twice that distance. And what is that? 120.7. And it doesn't matter where we start that change of time of 2. We can start it over at the left, we can start it in the middle, we can start it at the right. If we let 2 hours go by in constant rate of change, it'll always mean a distance change of 125.7. Equal changes in time result in equal changes in distance. Constant rate of change. Okay, and so from this, change in distance is always, can we always calculate the change in distance? So we can think about what is our constant multiple that gets us the change in distance given a change in time.
Delta t times 62.85.
Yeah, so our constant multiple is 62.85. That's that constant rate of change. We can always take a change in time and multiply it by 62.85, and it will give us the change in distance. So this is proportionality of the changes. When you have proportionality of the changes, you have constant rate of change. Now, what if we're interested in, so now I'm going to change to blue. What if I'm just interested in just these quantities of d and t, and we want to know for a given change in time, or sorry, for a time since she's left the home, how far from home is she? So what we can do is we can just say, let this be any point. So this is a roving point. So its coordinates are t, and the corresponding distance from home, d. So this could be anywhere along here. It doesn't necessarily have to be close to 2.5 hours. It could be anywhere. So what we want to do is we want to come up with a way of expressing, given this time since she left home, what corresponding distance from home is she? Do you see that that's different than this? This is starting at any time, given a change in time, what's her change in distance? Now we're saying, given a time since she was at home, what distance is she from home? That's different than this. So how do we do that? Well, we can use all this stuff that we're learning to do that. The first thing we want to look at is we can pick a point. So we pick this starting point that we know at half an hour and 25 miles from home. What is the change in time from that to t comma d? So we can start with what change of time is represented if from 0.5 hours to t hours. What change in time is it?
T minus 0.5.
He's offering up t minus 0.5. Agree with that? That's it. So there's our start. So to any time t, the change in time starting at half an hour to that time t will be t minus 0.5. All right, now we're going to use our proportionality of changes. What is change in distance?
t minus 0.5.
Okay, what we want it, but in terms of delta t. So what's the change of distance in terms of this delta t that we just found?
62.85 delta t or t minus 0.5.
Right. So if we always, the change in distance is 62.85 times the change in time. Here's our change in time. So we got 62.85 times delta t. And what's delta t? T minus 0.5. That's the corresponding change in distance for this change in time, for half an hour to time t. Does it make sense so far? So all we have left is, what was our goal? Our goal was, what is d given t? So, in general, d is equal to the d that we started at plus the change in d. So let's see if I can see. So we found, not bad. Okay, we just said this. The change in t is t minus 0.5. And now we said that this change in distance is equal to 62.85 times that. So now how do we get the new d? So how can we write an equation that will give us the value of this new d? Somebody new? How about someone in the back? What can we do to get this value of d right here related to all this stuff that we're talking about? It just should make sense. How would we get this? So think of this as the new value of d. How do we get the new value of d? Yeah?
Isn't the 25
Mm-hmm.
plus the change in d?
That's it. It's the old, right, it's the starting value of D, the old D, plus how much it changed, right? And what was the old value of D? 25. And how much did D change? 62.85 times the change in T. So that right there is a way to express the distance from home given any time from home. So given any time from home, given an x-coordinate on this graph, this will give us the distance from home, or the y-coordinate, vertical coordinate. So now we look at that. Are the quantities T and D proportional? Are the quantities T and D proportional? Yes or no? Is D a constant multiple of T?
Yes.
Can we write it as D equals K times T? So we can rewrite this. Let's do it up here. So D equals. So we can combine the 25 and the 62.85. So multiplying this out and combining like terms, we get 62.85 times T. I think you end up getting, so someone do this. I think it's minus 6.24. Is that right? Someone do this. 25 plus 62.85 times negative 0.5. So I'm simplifying this expression. I'm expanding it and then adding the 25 plus the 62.85 times negative 0.5. I think it's negative 6.24. Someone check that.
Negative 6.425.
4.2. 4.2.
Well, 4.3 if you round.
4.3. Great. Thank you. So this turns out to be the same thing as 62.85T minus 6.43. Same thing, just a different form. Are D and T proportional?
Yes.
Is D a constant multiple of T?
Yes.
What's that? Why not? Who? What's that?
Because their ratio changes.
Yeah, the ratio. So set up a table if you're not sure. But if you set up a table and start comparing the ratios, they're not proportional. What's causing them to not be proportional? This minus 6.43 right here. Because of that, D is not a constant multiple of T. If that was gone, it would be. But we got this minus 6.43. So changes are proportional. That's why we have a linear graph. Okay, constant rate of change. But the actual quantities themselves are not proportional. Okay, so now you can easily find how far is she from home at 3.3 hours. How would you find how far she is from home? 3.3 hours since she left home.
Just substitute 3.
Yeah, just this equation tells you, given any time, say 3.3 hours from home, just tells you how far she is from home. Questions on this process? So this process is very important. So really what this is about is taking our understanding of constant rate of change and changes and putting symbols to it, because that's what, understanding the language of math is key in calculus. And so we're trying to put good symbols, good notation to represent our understanding of what's going on. Okay? So that's why. So if you see a different way and you say, oh, it's much easier than this. You just do this and this and this. Well, your reasoning is probably very good, but we need symbols to represent. So that when we communicate as mathematicians to one another using calculus, we need symbols that we all agree on. So this is a lot of what this is about. Questions on this example? Okay, that turned out a lot better than the first class. First class I ended up with a mess, so this turned out a lot better. Okay, let's look at the example you did with the candle example in your homework last night. Okay, so here's the situation. The length of a burning candle decreases at a constant rate of 2.2 inches per hour. The candle has been burning for 3.5 hours and is currently 8.3 inches long. First, we want to represent, I kind of glanced at some of your work on this, represent an increase in the time spent burning of 2 hours from the given point on the graph. So starting at 3.5 hours, we want to represent an increase of time of 2 hours. How do we do that? Okay, so a change in the horizontal quantity means a horizontal line segment. So that horizontal line segment right there represents delta t equals 2. You need a horizontal line segment. That represents that change in time of 2 hours, starting at 3.5. So that puts us at what time? 5.5 hours. So if we change the time by 2 from 3.3, we were at 5.5. That's the time in question. Okay? So then it asks, how much will the length of the candle change when the time spent burning increases by 2 hours? So just use common sense. How much will the length of the candle change if it's decreasing 2.2 inches per hour? Yeah, common sense, right? But we want to put symbols and notation to that. So we do that by looking at, let's see, over here. Changes in time and changes in length. In 1 hour, what's the change in length?
2.2.
So should I write 2.2 here? So we want to be mathematical. Why is it not 2.2? It's getting shorter. So we need a representation of decrease. What is that? Negative. So then in 2 hours, you said it goes down 4.4. So or negative 4.4. In 10 hours, negative 22. Okay? So we're looking at the length of the candle is going to go down 4.4, and that's delta L. That's delta L. And we can represent that on the graph. How? 1, 2, 3, 4, that. So there's our delta L, and it was negative 4.4. Negative's important. So because then you can look at the number and know increase or decrease, right? You could, if we didn't use negative or positive, then you wouldn't know if it was increasing or decreasing. But by using negative and positive, it tells us. Negative tells us decrease, and positive tells us increase. And we got that by oh no, so that would be this. So what's the final length of the candle then? L would equal? It's the old L plus the change in L. It's common sense. And so it's 8.3 minus 4.4. And it is 3.9. Okay? And so we can represent that change in L of 4.4 as negative 2.2 times the change in time. Because constant rate of change means the changes are proportional. So changes in L in this problem are always negative 2.2 times the change in time. So we answer all these questions that I've got, A, B, and C now? All right, so let's go on. Okay, so represent a decrease of 1.8. So represent a decrease of 1.8 on the graph. In the back, in this corner, tell me how I'd represent a decrease of 1.8. Yellow shirt, right there, with the logo. Yep. No, up here in front, behind the hat. I'll just wait for him to. Yeah. How would I represent a decrease of 1.8 hours? What's that? What kind of line? Horizontal or vertical? And going which way from 3.5? Left, that's it. And I'm going to go 1.8 hours. What time will that put me at? 1.7.
Oh, it says you're dropping 1.7.
No?
Oh.
Decrease of 1.8, right? Decrease of
Sorry,
1.8.
I was reading it off.
So what would delta T be? 1.8?
Yes.
Not 1.8. Not 1.7.
Negative.
Negative 1.8. Remember, negative means decrease. Okay, so now using this, we can get the change in L. So our delta T is negative 1.8. So you all know, so every hour it's changing 2.2. We got 1.8 hours, so you multiply. That's it, 2.2. But this maintains the sign because you got negative 2.2 times negative 1.8 is what? Positive 3.96. Does it make sense that it should be positive?
Yes.
Because?
Negative times negative.
No, in the context. Why should it be positive?
Oh, you're
Because
adding
you're increasing
We're going back in time, so the candle should go
higher.
the higher.
up. If you go back in time, the candle should grow longer. Okay? So, and how much is that? How much does it grow? 3.96. 1, 2, 3, right about there. So that delta L is negative 2.2 times our negative 1.8. And that equals 3.96. New value of L. So what's the new value of L? The old value of L, 8.3, plus the increase, 12.26. Okay, so now that's the length at 1.7 hours. When we go back in time, negative 1.8 hours. So then part G is to find the height of the candle at the beginning, at 0 hours. So I want you to use the same process, the same reasoning, and same symbols in part G. Oops. Not what I meant. Here, this. There we go. So now, you do the same symbols, same process to find how tall the candle was when it started burning. So copy the same process. Take a minute to do it. Go, and then you can work together. All right? Talk amongst yourselves. Practice this process of using the symbols, using the delta symbols. That's what we're doing. Okay, I'll make one lap for questions. Got questions? Practice this is using the symbol. I want you to practice thinking through change in time, change in length, new length. Change in time, change in length, new length. But we need symbols. Calculus, you gotta have symbols that represents your reason. So that's what we're practicing. We're practicing using the symbols. sure your reasoning is awesome. But really, I would guess if you explain it to me, it's going to be the same thing. It is. So, but we're practicing using symbols. Practicing. Yeah, so the key thing here is many of you you're using good reasoning in your head and you know how to get these answers, okay? So the key is, can we make a bridge, right? So we want to maintain that good reasoning, but then we want to also be able to represent it really well. So we gotta find that common ground, okay? What I don't want you to do is just memorize some kind of series of steps that I'm doing, okay? So I want you to attach your reasoning to the symbols that we're using. First step. If we're interested in finding, so you could start from either place. You could start from here, or you could start from here. Where do you want to start?
There.
The first place? Second, this one. Okay. So what will we do first?
We're going from 3.5 to 0, so the change in time is -3.5.
Good. So the change in time, 0 minus 3.5, which equals? Negative 3.5. There's a blue change in time, negative 3.5. And so if 3.5 hours are going by, how much does the length of the candle change?
-3.2 times.
Yeah, so it's 2.2 times 3.5. But in this case, the 2.2 is negative, and the change in time is negative. So that gives us an increase of what? 7.7. So it was 8.3. And if we go back in time, 3.5, it's going to go up 7.7. So what's the new L? It's going to be the 8.3 plus the change in L, which is 7.7. Okay, and so then, as time goes by, we could find every point, right? What is a graph? It's a collection of points representing, each point represents a time and a corresponding length. The blue one would be the graph of the candle decreasing at a constant rate as time goes by. Anybody have a question? Okay, so what if we want it, so we've got the equation for changes in L and changes in time. What if we want the equation of length and time like we did before with the driving on the highway with Sarah? So we want length equal in terms of time. We could start here and we could pick any time t. So use the process again to come up with L in terms of time. If we start at 3.5 hours, 8.3 inches, and we go to any time t, you derive the equation that's L in terms of t. See if you can do it. Go. See if you can do it. Same thing. But now just this is a roving time. It can be any time. So now we're coming up with the equation that if we plug t in, it would give us L. See if you can do it. make the lab for questions. You all should be able to do this. So it's not 6 point whatever I'm saying. T can be any time since it started burning. T can be any time since it started burning. So you just wrote down y equals mx plus b. I'm asking you to work through the process again, to practice the process. Yeah. Yeah, so I'm trying to teach you something new, right? This is class where you learn something new. So you can use your old way, but then you wouldn't have to be here, right? So I'm trying to teach you something new that's very powerful. When you get to other situations, you can use it, and it's very important in calculus. So let's try to find some middle ground here, right? It's class. We're going to learn something new. Okay. Okay. Did anyone have success? Tell me in the blue shirt.
Negative 2.2t plus 16.
That's an answer. I'm looking for a process.
Oh.
No, it's okay. But that's an answer. I'm looking for a process. Did we learn a process of reasoning? Yeah, orange.
Okay, so I started off at 16 because the beginning is 16, and then there's a change in t, but we're trying to find length. So I said 16 minus the change in t times 2.2 because the change in t is multiplied by the 2.2 since.
So 16 minus the change in t. Like that?
2.2 because every hour changes 2.2. Or no, not it just starts 16 and then minus the
Just delta t is nice.
It's not like that.
Okay.
That's not how
I was just writing down what you said.
because I begin at 16, right? And then so every hour it's minus 2.2. So I say, let's say 16 minus and then parentheses delta t. Or I guess 2.2 minus
So
delta t parentheses 2.2.
okay, did we? Yeah. So it's one more time. 16.
16 minus delta t parentheses 2.2.
Okay, except that we want L in terms of t, not in terms of delta t. So we want L in terms of t, not
Or
delta
t. I
t.
should just say t.
So did anyone start with our point here, 3.5 and 8.3?
No, because you're trying to find a formula for any point during the timeline. So I don't know where to start.
No, that's what we wanted to do. So if we hadn't found this point, so we wanted to start at this point. Did I say that? That's what I meant. So starting at 3.5, going to any time t. What's that?
If you start there, you can go over 1 hour to find the slope, which is 2.2, and plug that in the y plus mx plus b. So what I did is I used y plus mx plus b. Y and x are L and t respectively. The slope is 2.2. You find that by going from one point to the other. And
Okay.
t is the y-intercept.
Right. So I'm hoping that you wouldn't use mx plus b. Okay. So
Did you use
that's
the
okay.
formula that we had last time and then just switch some things around? Which the delta.
So let me. Okay. So you may all have very valid ways of doing it. I'm trying to teach you a new way. So let me. Can I? Well, I'll just do it again. You should starting at 3.5, 8.3. Let's find the change in t to any time t. What would that be? Starting at 3.5, 8.3. Would the change in time would be
t minus
t minus 3.5. This is what we've done. What would the corresponding change in length be since we have proportionality of the changes? So for any given change in time, the candle goes down to negative 2.2 times that change in time.
Yeah, that's what I did.
Okay?
And I got, if you multiply that out, you get L is minus 2.2 T plus 7.7.
Okay, so from here, how do we get L then? So from here,
You distribute minus 2.2.
we could, but we can just leave this as the change in L. Okay, so what I wanted to show you was that the new L is the old L plus the change in L. Remember that? So the old L is 8.3. And what's the change in L? This expression we just found. Negative 2.2 times t minus 3.5. I know, you're all convinced. Your way is better. You're all convinced, I know. Okay, but we start with a change in t from a point that we know. We can get the change in L by taking negative 2.2 times that. And then we have the change in L, so we've got the old L plus the change in L. Gives us the value of the length given the value of the time. Okay, anybody have a question? So if you can make a bridge to the way you understand it, to the way I'm trying to show you, that's what we're going for. So someone, can you understand what I'm doing here and make a bridge? Okay?
This is L in terms of the 1 point that we're given, and then moving down.
So this t can be any t, right? So this t is roving, so it can be any value of t.
Between the point that we have and
No.
past, no?
It could be negative. So if t was negative, then you would, I'm sorry, if t was 1 or 2, it would still work. Because then this would be negative,
Yeah,
and that would be positive and would be going up.
yeah, we're just using those numbers because that's the point given.
Right. I was just using this point given.
Okay.
Okay, we'll not see you on Monday. So the assignment, we're going to have a written assignment like Wednesday, so due next Wednesday. Have a nice vacation.
I'm sorry. I'm struggling.
Hold on a second.